Okay, a few things that I want to point out, a few things that are not a vector space. So, a few things that are not a vector space. Let's start with an example that we alluded to before. If I were to take the set S to be the set of polynomials of degree exactly 2, so ax squared plus bx squared plus c, ax squared plus bx plus c, where a, b, and c are real numbers, and where a is not equal to 0. Okay, this is not going to be a vector space, and the reason is that it's not closed under addition. If you add two polynomials of degree exactly 2, you don't necessarily get another polynomial of degree 2. So for example, if you were to take one polynomial which would be, say, x squared plus x, and another polynomial which would be, say, negative x squared, when you add these two polynomials, what are we going to get? Well, f plus g is going to be x squared plus x plus negative x squared. So of course we just get x. But x is a first degree polynomial. So somehow when we added two elements from our set S, we got something that was outside of S. Okay, so that is against the rules. In fact, that's against rule number 1. So let's just go back and look at the rules. This is against what's called closure. Okay, so I should add that this is called closure. If we add two vectors, we should get another vector in the space. Here we did not. We added two polynomials of degree exactly 2. We got a polynomial that was not of degree exactly 2. Notice, however, that what I said before is what is a vector space is the set of polynomials of degree at most 2, or in general, the set of polynomials of degree at most n. And it turns out that if I add two polynomials of degree at most 2, I do get another polynomial of degree at most 2. In this case, it's a polynomial of degree 1, but that's fine. Okay, so that's why the set of polynomials of degree exactly 2 is not a vector space, but the set of polynomials of degree at most 2 is a vector space. So there's a reason why we had to define it like that. One other example of sets that are not vector spaces is the set of integers. So for example, so we could write this as you could think of this as the positive and negative whole numbers and 0. 0 is not positive nor negative. And this is a set that's not closed under scalar multiplication. Remember that what the rule says, and this was rule 5 or 6, rule 6, it says that if I take any scalar, any real number, and multiply by a vector, it should stay in that space. But that's not going to work for the integers. So for example, if we were to take any real number, say pi or square root of 2 or e or even 1/2, and multiply that by, say, 3 or 2 or 1, say pi times 2 is not in S. That's not an element in S. And therefore it's not closed under scalar multiplication. Okay, so there's another example of a set that's not a vector space. And then there's others. For example, we could talk about another set that's not a vector space. Let's call it S. And so let's say that this is the set of real numbers of the form x comma 1, where x is a real number. Okay, so this is not a vector space. And it turns out it's not a vector space because, again, it's both not closed under scalar multiplication and vector addition. So for example, if we were to pick, say, 2, 1 and 4, 1, those are both in S. Okay, so let me write this a little bit better. So 2, 1 is an S, 4, 1 is an S. But if we add them, 2, 1 plus 4, 1, and I'm sorry, I'm just realizing that I'm reverting back to what the book does without explicitly saying it. So let me actually write these as vectors if you'd like. So this is the set of vectors x1. So let's take the vector 2, 1 and the vector 4, 1, and those are both in S. But when we add them, we get the vector 6, 2. Since the second coordinate is not 1, it's not an element of S, and therefore it's not closed under addition. It's also not closed under scalar multiplication, because, for example, we could take 2, 1, multiply by 3, and we would end up with 6, 3. That's also not an S because the second coordinate's not 1. Okay, so that is not a vector space. Okay, so let me just emphasize that this is, so S is not a vector space. Okay, so that's what we emphasize there. The same was true of the other examples. So here, S was not a vector space. And here, S was not a vector space. On the other hand, if I were to modify the last example, S, and say it's the set of vectors whose second component is 0, then this is a vector space. Okay, this is a vector space. And you can check that all 10 properties are there. So it's closed under vector addition, it's closed under scalar multiplication, because when you add two vectors whose last component is 0, the second component of the sum is going to be 0 plus 0, which is 0. And if you scale it, you're going to get c times 0, which is also 0 for any real number c. So it turns out that those two properties are satisfied. All the other properties are satisfied as well, and we'll give some nice, easy conditions to prove that that this set is a vector space. We'll do that in the coming videos.